So in this particular lecture, we're going to be looking at how to implement all what I already explained in the previous lectures in R. So first of all, you need to have this particular packages installed. We have the mass package. So we're going to be using the step AIC function from the mass package. And also we have the car package, which is for VIF calculation. Then we also have ggplot2 for visualization. We have dplyr for data manipulation. We also have grade extra for arranging plots. So if packages are installed, you are going to if you already have the package, if you don't have the packages installed, you install them using this particular command, install.packages. So but if you have them installed, you don't need to install them. So I'm going to be using the birth weight dataset from the mass package. So I'm just going to load the data, and once we load the data, we just have a view of the first few rows of the data. So I already have the lab in the GitHub repository, so you should be able to see it there. So when you look at it, you can see this is just a preview of the data. You can see we have the first column. We have you can just check for the birth weight to check the meaning of these columns. So we just use the question mark with the birth weight name. So you can see this low is the indicator of birth weight less than 2.5 kg. So less than 2.5 kg will be assigned the value of 0. Higher than 2.5 kg will be assigned the value of 1. Then we have age, which is the mother's age in years. We have LWT, which is the mother's weight in pounds at last menstrual period. Then we have the race. You can see it's just 3 levels: white, black, or other. Then we have smoking status, which can be 0 or 1. The PTL, which is the number of previous premature labors. Then we have HT, which is the history of hypertension. We have UI, presence of uterine irritability. We have FTV, number of physician visits during the first trimester, and BWT, which is the birth weight in grams. These are the various variables which we have in this particular data set. Okay, so the first thing I want to do now is to, first of all, we're creating a working data set as birth data. Now we convert categorical variables to factor, with meaningful labels. So our race now, we're going to convert it to categorical, just to run this. So if we should take factor now, or if we check levels of the birth data, race, should be able to have white, black, and other. Same thing also, I'm going to convert the smoke variable also to a factor with 2 labels, which is non-smoker and smoker, and also the hypertension, 2 labels, which levels no or yes. Then we also have the UI, which is the uterine irritability, as 2 labels. Then we now take the summary statistics of our data. So based on our summary statistics, so this is what we have. So these are summary statistics. Low, we can see these are for the variables that are, these are some of the variables we have: low, age, LW. So you can see for the values we already assigned categories to, we cannot see because some of this particular low is supposed to be categorical data also. So but we have not assigned labels to it. We will convert some of the ones we're going to be working with, like race, smoke, HT, and UI. As you can see them in this place: smoke, race, HT, and UI. So you can see it. So the rest you can actually do that on your own. So let's check for missing values in the birth data. So our data set is very complete without missing values. So now for a simple linear regression, now this is just a simple linear regression which is single variable for age. So I'm just going to run this. I already explained about this earlier on. So you can see this is the BWT. So I told you that the BWT is the birth weight in grams, which is the outcome. The outcome is going to be on the left hand side, while the predictor will be on the right hand side. So age is now going to be the predictor. So if you look at our model in this place now, you can see that our the estimate of the age is 12.43. We have the error time of 10.02. We have the t-value 1.24, and these are p-value. So it's not actually significant. So, but assuming age was significant, it means that for every unit increase in age, then the birth weight is going to be increasing by 12.43 units. So this is just what it signifies. But this is not actually significant because you can see it is what greater than 0.05. So now let's check our R square too also. Let's see what do we have for our R square. Our R square, you can see is very low, which means that the variation of the outcome explained by the predictor age is around less 0.8%. So now let's construct the multivariable regression. This time around now we're adding we're controlling for other factors now, like the low weight, so the mother's weight in last menstrual period, the race, the smoking status, PTL, HTUI, and also the FTV. I'm just going to run this, and when we run this now, you can see we have our full model. So we have that of age. You can see now we have for age, the estimate has already changed because I've already controlled for other factors now. So it's like we've already controlled, there's possible confounders in this particular other factors that we have. Now, you don't forget that race is actually a categorical variable. So don't forget that race is actually a categorical variable. And we have smoking status also as a categorical variable. So race, the reference variable for race is going to be white. You know, we have 3 levels under race. A smoker is going, the non-smoker is going to be a reference variable for smoking. Then PTL, then for hypertension also, someone that is non-hypertensive will be the reference variable. So reference variable means the person, the level variable we are comparing with. So for the explanation of these coefficients now, you can see that the age is, let's start with the age now. So for every unit increase in age, then the birth weight is going to reduce by minus 3.570, and you can see that this is still not significant because the p-value is greater than 0.05. Now for also the mother's weight at the last menstrual period, you can see the coefficient is 4.354. so for every increase in the mother's weight, the birth weight is also going to increase by 4.354, which is actually significant because it is less than 0.05. Then we have the race, which is currently we have 2 categories, race black and race other. So you can see that in terms of the women that are from the black race, so their birth weight is going to reduce by 488.428 compared to those that are from the white race, since white is actually our reference category. So this is the p-value 0.001349, which is less than 0.05. Then for race order 2 also, their birth weight is also going to be reduced by minus 355.077 compared to women that are from the white race. And you can see this is the p-value 0.002290, which is also significant because it is less than 0.05. Now we also have the PTL. So PTL is the number of premature labor. So for every unit increase in the number of premature labor, then the birth weight is going to decrease by minus 48.402. And you can see it is not actually what significant. Also, we don't forget smoker. Smokers are actually going to have a reduced birth weight of minus 352.045 compared to those that are non-smokers, and this is actually significant based on the p-value. Then we have hypertension. So those that are hypertensive will have a reduced birth weight of minus 592.827 with a p-value of 0.003830, which is actually significant. Those that have uterine irritability, they will have a reduced birth weight of minus 516.081 with a p-value of 0.000271. Then we also have FTV minus 14.058. Any unit increase in FTV, then the birth weight will reduce by minus 14.058. But the p-value is not actually significant. So if you just look at this now, you can see that these are the various coefficients that we have in our data, and these are the ways we can interpret it. So if you look at the R squared now, so you can see the R squared 0.2427, the adjusted R square 0.2047. So which means around 20.47% of the outcome was explained by those predictors. So the R square is actually poor, is not high, which means we might need to consider other factors, because with the amount of factors we have here, it still explains 20.47% of the variation in the outcome.